Hello, everyone. So, any one of you tried the YOLO library in Elixir? Nice. Okay, nice. So, the talk's goal is to see how to run in Elixir object detection and object tracking. First with the YOLO library, and then see how to fine-tune a model with the custom dataset, and also how to run object detection on edge devices like Raspberry Pi. And so this Raspberry Pi here, which is the 5 with the Hailo-8 Hat, which is this model here, connected via PCIe. Yeah, which is called the Hailo-8. And then see how to run object tracking and the work I'm doing for object tracking in Elixir. So first, what is object detection? So object detection solves two problems. The model solves two problems at the same time: localization and classification. Localization is to get the bounding boxes for the detected objects. So we give an image and we get the bounding boxes coordinates, and then also classification of the found objects inside the bounding boxes with a certain confidence, the probability. So here we get for this object, which is a track, xy, and the width and the height of the bounding box. So usually these are floats, and there are number between 0 and 1 because they are relative to the whole image size. And then we get the probability distribution for all the supported classes. So in this case, 70%. Usually we get a float, a number again from 0 to 1. In this case, would be 0.7 for a track. There are many, many uses. So it's used for manufacturing, data detection, security, sports and media to track, for example, the players, healthcare, and especially automotive. For example, for ADAS, they are part of the ADAS, parking and tolling, and dash cams, and many other uses. This is this is the platform of the company I work for. It's what we do. We extensively use object detection and tracking to understand all the surrounding and understand the events, like, for example, missed collision, missed red light sign, or stop sign, and to also understand people crossing, bicycle, etc. So there are many object detection models. The most famous right now, at least, is YOLO. And this was the paper that came out in 2015. There is a YouTube video, I think it was a TED Talk, related to this paper, and the author of the paper shown the first YOLO version. And what came out, so the important thing, the revolution of this model is that it was able, with a single pass of, with a single inference from the image to the end of the model, to give two things: the bounding boxes coordinates and the classification for each bounding box. So with a single pass, we got these two things. Reason why is called "you only look once." So the library I built this YOLO library. You find it also on Hex. And so the goals of this library are mainly two, actually three. The first is to be super simple. With this just two line of code, actually there is YOLO load and YOLO detect to run detection. So really simple. And the second is to be really fast, at least as fast as the Python alternatives. And the third is to be extensible. So you just need, if you want to implement a new model, you just need to implement this behavior, pre-processing and post-processing, and the init. Right now, the inference is the library itself takes care of the inferences, but probably in the future, I will introduce also custom inference. So it supports the ONX format because at the moment is based on the Ortex. So Ortex is a ONX, so it's a NIF, uses ORT, which is a Rust library which runs the ONX runtime. The cool thing is it has a huge number of execution providers, meaning we can run these models on a huge list of different type of hardware, like CUDA, TensorRT, CoreML. So for example, CoreML is this computer here, a Mac. CUDA in case of you have an NVIDIA, or like a Jetson Nano. If you have a Jetson Nano, you can use this library straight away. The near future implementation, so I'm working on object tracking and segmentation, and also re-identification. We will see in a bit. So we saw that the callbacks are pre-processing and post-processing. The reason is that what this library does is to, sure, run inference, but the pre-processing and post-processing are really tedious. We can't just input the image as it is with any kind of resolution into the model and then get the output and we have our bounding boxes. Unfortunately, it doesn't work this way. So we have to normalize the image, rescale it, add some padding if needed, and then each model, a different model, needs a different kind of pre-processing. And the output is usually we have this 8,400 detection candidates, so the number of detection candidates, and 84 columns, which are, in this case, a model trained on the COCO dataset with 80 objects, and 4 are the columns for the values for the bounding boxes, X, Y, W, so width and height. The post-processing is running on NX mostly, and what it does is running this NMS. Is basically deduplication, is basically a filter algorithm to remove part of the duplicates. So yeah, just to say that pre-processing and post-processing are quite important, and it's important that they run fast because they add delay. So the two main models you see around right now are, well, the most famous is Ultralytics YOLO. There is the Ultralytics company behind, and the models you find around are under AGPL plus enterprise licensing. Reason why I've introduced this YOLOX support as well, also with some contributions because, yeah, obviously the library is open source, so there are other people that help me out. The cool thing about Ultralytics YOLO is that the tooling is great, especially for fine-tuning. They have great tooling. So go for it, especially if you want to run prototypes and to run to make prototypes, and then you know that you can have alternatives. These models, the models you see around, are based mostly they are pre-trained with on the COCO datasets. You see that there are 80 common categories. Like cats, dogs, but also something like useful that we can use on the road, cars, bikes, trucks, people, backpacks, and yeah, time for a demo. So here, just to show you how easy it is to, so I have a live book, and I don't know if you saw the first slide at the beginning. I've put all the demos. I'll try to run all the demos, but you find all the demos here. The live book I'm going to run, and the YOLO track and YOLO detect, which are two Scenic Elixir applications running with Scenic. So this is, let's see if I have, yeah, okay, this is running. So we include, to run the YOLO library, we just need to include it, NX and XLA. Then it supports both image and eVision. And here I'm including Kino and Python X, but not because we need Python, hopefully. But because we need to, so we need Python and the Ultralytics library just to get the model. We can download the model also from this website. This is the Ultralytics official assets repository. These are PyTorch file models, and we need to convert them to on and X. So what this script does is simply to use the Ultralytics YOLO library to convert, to export the model to ONNX. We are right now using the YOLO 11N. Okay, so what it's doing is to create the, you see that I had YOLO 11N PyTorch, and now I have also the YOLO N ONNX. So I'm not cheating, I'm doing it live. So I'm just loading the model, super important in both here in the configuration to, so the library uses NX for pre-processing and post-processing, so be careful to configure NX correctly, and also Artex, which is the inference runtime, the inference library. Here in this case, CoreML for the Mac. And again, here when we load the library, we need to specify the execution provider. In case of a CUDA, instead of CoreML, you use CUDA or TensorRT. So let's load it. And here we have some details. 640 by 640 is the input, and the output is this famous tensor here. So let's get an image. You can notice that there are really, really small objects, well, in this case, people, but these images are resized to 640 by 640. So it's incredible. You will see that it should be able to detect also that person. And in a 640 by 640 image, it's like probably a few pixels or 1 pixel, because it understands the context as well. So we get the output of the function, actually, of this second function here, is this list of maps. If we use this function, we get a list of lists. This is just to convert that list to something more human readable. And then we use this function to, this helper here, Kino YOLO, to get the results with the people, so with the classifications and bounding boxes. Let's see something live. So I'm using this camera here, and let's see. You see that it's straight away. So, okay, is refrigerator? Probably not, but it's, you see that the percentage, the confidence, I don't know if it's big enough, but it's 30%, and hopefully it detects me as a 94% as a human. So, yeah. But these are just still images. I could use Livebook to render a video like with detection, but it's far better for rendering to use a Scenic. Anyone knows what Scenic framework is? Okay. So Scenic is this thing here, is a framework. So is a library to render, to create applications with Elixir. So for rendering this type of stuff, so videos and bounding boxes is great because it renders the frames with some hardware acceleration. I don't know the details, but it's definitely faster. So you just need to go here. You find it in the repo. And the code is pretty much the same. Basically, it's an iteration. So get the image, classify the image, and sends and renders the results. In this case, I think I'm running a large model. So let me just see and change. You see M here. I could use N. N will be definitely faster. N stands for nano, M for medium. And it should work. It takes some, and you see that it's super smooth. And this is a MacBook here with an M3. So yeah, nice machine, but not the best. And I'm running at 50 frames per second. And the cool thing is that on this thing here will run even faster, like around 100 frames per second with this model. With the M model, it's around 30 frames per second. So enough for at least for what I need. Great. So yeah, what about edge devices? Just a second. Okay. What about edge devices? So as I said, we can run on the Hailo-8 or 8L. So the L is the cheapest version with the 13 tops. And the Hailo-8 it's twice as fast as this model here, and you put it on the top of the Raspberry Pi, and the energy consumption is really low, all considering. Reason why we could need to run these vision models in general on edge devices, because sometimes we can't afford the latency of network. We need faster decisions, especially automotive and transport. Or sometimes we don't have an internet connection. We have poor connection, and sometimes for privacy, we really can't send the data outside the device. So for this, so right now the YOLO library doesn't support this device, but you can use this NX Hailo that was built by Vittoria, Bitton, and Paulo Valente. It's a NERVS firmware. So there is everything. You just need to go to the repo, and there is a great documentation. Especially the documentation is live books. So just take a look at the live books. And it's super easy to flash. It's ready to flash. When you compile the firmware, it downloads the model, and then you're able to flash it and use and connect with the live book and use it. The models are different. You see these HEF models, meaning there is this Hailo format. It's a bit of a pain to convert ONNX or any kind of model to this format, because the models need to be quantized. So there are on this website here, if you want, these are official from Hailo. There are many models, classification, object detection, even segmentation. You can run segmentation on this device pretty well. I mean, it goes fast. And the performance is quite, as you can see, great. So that is frame per second without batching. The other column on the right is with batching, I think 8 images, batches of 8 images. So why it's faster than this? Because the models are quantized. So this is using float32 model, and that is using int8. So the main reason is that we lose accuracy, but just a little bit of accuracy to quantize the models. But they go quite fast. So let's see just a little bit how to fine-tune one of these models, because I think this is probably the most interesting things to try out these models. Sure, it's interesting to detect myself, but to create prototypes, this is the way. So I'm going to, in this case, I'm going to show you how to get like a data set, in this case for hands, and then train a YOLO 11N, which is the nano version, and get a model that you can use straight away with the YOLO library. RoboFlow Universe is like a portal where you can search data sets. So I found this data set with around 9,000 images, which seems great. So 9,000 images is a really good start for fine-tuning. The problem is that this data set was okay, but it's not. We don't see a lot of variety. You see that in every single image there is a black background. So the results are not that great, but you see that this data set is far better because we have a far larger variety of situation and hands. So this is definitely a better data set. The problem is that so there is a working link to download it, but yeah, I didn't have the time to train another model for this. So especially because I think RoboFlow Universe is a good start to start getting data and getting good data sets, especially because you can export the data set with the format you want. And then with the Ultralytics, so this is part of the Ultralytics library, you just need to run. So install, obviously, the Ultralytics library. You run YOLO train data. Data YAML is a file you find inside these training data sets when you export from this. Reason why it's really important to get the right annotation format. And then the model. So why we need a model? Because first, we need to understand which architecture. And second, because we fine tune. Usually we don't train from scratch. What we can do is to start from a pre-trained model, use the knowledge that is already built inside the model, inside the weights, and just add our training on the top. This means that we can use just a few, here I don't have the number, but we can train the model with just a few thousand of images and get good results. In case of training from scratch, we would need a much higher number of images. So when you train a model, this is actually an image that comes out at the end of the training with that tool. And the important parts are validation losses. So the losses in general, on validation data set, they need to go down. And the MAP, which is mean average precision, needs to go up. Usually, it's better to consider the mean average precision with the IOU. It's called the 50 from 50 to 95, which is a stricter, a more strict matrix. And then we get this best PyTorch file, and we export it to ONNX format. So yeah, this is the result. You see that it's not great. I mean, it works. It works. It's not great. So I will be probably uploading this model, but train on the other data set as part of the repo. So what about YOLOX? Because it's supported by the library. So there is this. It takes time, much more time, and there is a YouTube video I made about it's 1 hour video about everything, how to fine tune the a YOLOX model from scratch and use it. Sorry. Yeah. So what about object tracking? So so far we're able to detect objects in an image, but we don't have any connection between frames. I mean, that car in front of us, it's just, I mean, it's the same car, but we don't have any idea it's the same car. So we need what is called object tracking. And as part of this talk and the repo, I've uploaded a simple, really simple approach, which is based on this idea. And the final implementation will be based on what is called the byte track algorithm. So the idea is that from this frame to the next, well, as humans, obviously, we're able to understand that it's the same object, and the bounding box is just shifted to the right. So what about considering the intersection? And OK, great. So we get the intersection area. We get the union area between the two bounding boxes. I mean, the one of the past and the current one. And then we get what is called, and this term is used over and over for NMS, for you saw the MAP 1595. 1595 is this intersection over union. And it's a simple thing, but it's used a lot. And it's the intersection over union basically is the overlap ratio between two bounding boxes. So just to show you now a tracker, so it's a simple track, and let's see how it works. And by the way, you find it here, also in the repo, and again, it's implemented with Scenic. Okay, it should be this. Yeah, I just go a little bit. Okay, so you see, in this case, just a second, I'm changing a parameter I wanted to change before. So you see that inside here in, okay, I just want to change the probability, the filtering probability here. Okay, these are parameters you need to play with. So you see here that I'm tracked. You see that one, I don't know if it's visible, but it means that it understands. It works because this is probably the simplest situation. And I am actually going to ask you if you can come. So as you can see, I'm tracked. And also now he's tracked. And you see that 2, 1. And if we move like this, it's pretty fine. I can do this. The problem is that when we have overlaps, this is probably the trickiest situation that byte tracks actually solves. So if I do this, you see that, OK? Thank you. So obviously, this is really simple, it's just IOU based using this trick. And the final implementation I'm working on is a little bit more complicated. It's based on the byte track paper. I put the link in the issue in the repo. There are many other algorithms. Still, it's just based on the bounding boxes, which is pretty interesting. It uses a Kalman filter to understand. So it runs 2 predictions, one with a Kalman filter, and the other one, the prediction coming from, the inference model, the YOLO model, and then tries to match, has these two things, and to understand if the object is the same. And something really cool I want to add is what is re-identification. It's not part of byte track. It's something we can use on the top. So what happens if we use many cameras, different cameras? We have, like this case, we have cameras around, and we want to track a person. and obviously we don't have the face of the person in our database, but we want to track the same person. Same for cars. We want to track the car. So what we do, and also we are in a store with a single camera. A person goes out, and after 5 minutes comes in again. What do? Obviously, for the system, for just by track, is a different person. So we use another model. This is not just something by track, which is not a neural network. It's a system. But in this case, we use a convolutional neural network to get an embedding of the person, but because there are many of these models for people, but it's possible to train these models also for cars or many other objects. And to get the features representing the person, the object, or the object. And every time a new object comes in, we try to understand if the person or the object is the same of the one we have in our temporary database. We calculate basically what we do with embeddings. We calculate the distance between the new object that comes in with our vector database. And that's it. So let me know if you have any question.
Thank you, Alvise.
Thank you.
Who is brave and has the first question here? I know like Alvise came from Italy and brought like half of the Italian community, it seems, here as well. So we have like, is it all the front row? I think those,
yeah.
I think 10, 12 people from Italy. That's great.
All around. In the other track, probably.
In the other track, there's more of them. Well,
great, but let me know. I mean, just that is my email, so you can ping me if you have any question or something you want to run.
Feel free to reach out to him. You can either find him or via swap card, ask a question later on. And with that, thank you so much.
Thank you.